Hello guys and welcome to the Procedural Microchip tutorial series episode 4. What's on the menu today? We are serving a well done extra crispy eprom window. What I used in the intro, the first part and also on the thumbnails of the previous parts was a simple cube with 3 extrusions that was cut out from the microchip. But it just felt like it was missing something, it just didn't feel right. An idea of a more complex shape was whispering in my mind. Go for it, give me beautiful rounded corners. And I have subdued to that idea. So there you have it, eprom window that scales with the size of the chip, has rounded corners and can be changed all the way to a circular shape. Let's not waste any more time, here we go! Okay, back to geometry nodes tab and let's make a space here, zoom out and we'll start somewhere above the pins cutout. Well, let's add a cube here. You can't go wrong with a cube. So let's add a cube. The size we will need RE combine XYZ. And the Z will be constant, so let's add here a value because I will need it as well later. So the height will be 1 millimeter. And the XY axis will depend on the size of the chip. Let's add here a viewer node. Now, for the width, I will actually need a group input here. Okay. I will map the chip width. I will use a map range and derive the value from the chip width from the minimum and maximum of that parameter or of that input. So let's search for chip width. It's 7.62 millimeters, the minimum value. So let's add here this value. The maximum is double. So let's write it like that. And since we have 7.62 millimeters, I think the bezel could be something around 1.5 millimeters. That makes it 4.2 millimeters, something around 4.2. I will use the value. I'm writing a nonsense here. Okay, that is 4.5 millimeters. And for the maximum, I think double of that value could work well. So let's plug it into X. And this one will also serve me as a unit for the dimension on the y-axis. What I will do is add additional input here, right onto the end. So let's go to end, add another integer value, and the name of it will be min pin count. So anything below that value will disable the cutter. The default for that one will be 10. So anything below 10 pins will not make the cutter visible, but that one will be solved later. Also, what I will use this for is to divide the pin count with this value. So let's add here a division and truncate this value. So if I have a pin count of 20, this one will give me 2. If I have 14, it will give me 1, the same as for value 10. For anything below 10, this will give me 0. Okay, and what I will do is multiply actually the value with the mapped width of the cutter object. So let's plug it into the y-axis, and here's our cube. Well, now what I want to do is to create these bevels or fillets on the corners of the cube. How to do that when there is no such node in geometry nodes? Well, we will have to be creative. First of all, we'll use a extrusion set to individual mode, and I will want to extrude all the faces except for the positive and negative z-axis. Well, for that, let's actually hide the side panel so we have more space. For that, I will use a compare node set to vector, and I will be comparing a normal of the face with a vector. First will be positive z-axis, and the other one will be a negative z-axis. So let's duplicate the comparison and change the vector to -1 on the z-axis. Well, to combine them, we will have to use logical AND, but actually what I need to do is to set this to not equal, because we will want everything that's not on the Z and minus Z axis. And to combine them, we will use a logical AND and replug it back to selection. Okay, those are the faces that we want to extrude. The extrusion scale will have to be quite small, so let's add here another value node with a value of 0.1 millimeter. Okay, maybe you see where this is heading. I will use a convex hull on this geometry, and that will create an object around the perimeter. Well, we still have a bevel, and I want a fillet. So let's duplicate the setup here and simply plug it like that. Use the same selection, and the offset scale will be the same for the moment, but that creates an uneven faces. So what we need to do is use a math node and multiply this value by 2. Not add, a multiply, and that will make the faces even. Okay, let's move them aside a little bit. 3 faces maybe could be enough, but I will use an additional extrusion and convex hull, because I want it to be a little bit smoother. So let's duplicate again the extrusion and the convex hull, replug it into a viewer, reuse the selection, and again we have to multiply. We have to either multiply this value again by 2 or the initial value by 4. So let's plug the offset scale here, and we have a beautiful fillet. But we are not yet finished with the extrusions, so let's duplicate the extrude mesh and plug it after the last convex hull. Let's disable the individual. And also, we don't need to zoom out, because we just need to decrease the scale. So I will extrude it with 1 millimeter, and the direction now will be on the negative z-axis. Well, we already have it, and the face, or I want to extrude the face that's on the negative z-axis. So you kind of already have it selected. We only need to invert it. So let's use a Boolean math set to not mode and connect the result to the selection. That will extrude only the face on the negative z-axis. Now, yet again, I will want to extrude a perimeter of the object. And for that, I will need again to use a compare node set to greater than. To the A socket, it will be connected face index. And I will compare it with a number that I have to figure out. So this is number Z, the phase number 0. So anything that's greater than 0, and let's search for it. Well, that's too much, so let's decrease it to 33. Okay, so anything that's greater than 33 will get extruded. So the basic cutter shape is done, but we're not finished yet. Let's get rid of the viewer here and actually plug that mesh into the boolean where we are cutting out the notch and also the cutouts for the pins. So that's all wrong. Well, first of all, it's too wide. That's because we added something by the extrusions to the original dimension of 4.5 millimeters, and also it's on wrong position. So let's solve that. Let's add here a transform geometry node and move that upwards. So let's add here a combine XYZ node. And we will be moving it in the positive Z direction with 1/2 of the chip height. So let's add here a multiplication node, multiply the value by 0.5 and plug it to the Z axis. Okay, we are getting closer. Now, also what we need to do is to add here a set shade smooth node. So we get rid of the flat faces, and now let's solve the problem with the with the thickness of the cutter object. We actually have to subtract all the values of the extrusions that we made for the convex hull. And that's 1 plus 2 times plus 4 times. That's total 1 plus 2 is 3 plus 4 is 7. And actually it's happening on both sides. So we have to multiply this value by 14. And subtract it from this value. So let's add here a subtraction, a math node. A math node actually, let's replug with Control click and drag the result here. Change the mode to subtraction. For the moment, let's put here 0. And I will need to multiply this value by 14. So let's multiply it by 14 and plug the result here. That should give us the width of 4.5 millimeters at the lowest chip width and the 9 millimeters at the highest chip width. So let's try to play with it a little bit. Okay, I think that's working pretty well. Now let's also change the pin count. Yeah, and the window size is actually increasing as it should. Let's return to 10 and change the chip width to the normal 7.62 millimeters. So if you start to play around with the radius factor, I guess, because it's not directly radius, and you get to value of 0.3 millimeters, you'll see that the cutout becomes circular, which is what we want. It will get a little bit squished if you increase the pin count to something like 40. It becomes sort of a oval. I don't mind that. What I do mind though is if you exceed certain limits of the radius, like 0.5 millimeters, the shape becomes too large for the microchip, so we will have to limit that. Also, if you decrease the value all the way down to 0, you will lose that pocket, so we'll take care of that as well. Let's add here a clamp node. Let's replug the value here, and actually we won't need that value node anymore. Let's change the value to what we had, like 0.1 millimeters. Minimum I will set to 0.015 and maximum will be actually variable. So for the narrower chip, it will be at 0.3 millimeters. So whatever we enter here, it won't get past that circular shape. Let's return it to 0.3 millimeters. But for the wider chip, we will need to increase the maximum to 0.6 millimeters actually, because that will create the circular shape for the wider chip as well. Well, let's actually reuse the map range node. So let's duplicate it. I will use again the chip width as the input value. The from values remain the same, while the to min will go through 0.3 millimeters to 0.06 millimeters, and that will serve as our maximum. So now if we have the narrower chip, the maximum will stay clamped at this value. Let's enable the value of the fillet for the group input. So I plug the value into an empty socket. Let's rename it actually, and also set up the values here. So the default will go at 0.01 millimeters. Minimum and maximum can stay as they are because they are limited by the clamp node here. And let's change the name to eprom window fillet. And since we are here in the group input, let's add here one more input. That one will be, that's the empty one, that will be type boolean, and the name of it will be eprom window enable. So we can actually disable the window here. Let's move it above the window fillet. And another thing I want to do with the min pin count, I want to actually hide it in the modifier so the user doesn't have an access to it. Now we can get rid of the side panel here, and let's actually get the eprom window enable switch working. And for that I will use a switch node. plugged here after the transform geometry, but I will utilize the true socket. So if that condition is true, the switch will output the geometry of the cutter, while if it's false, it will output an empty geometry. I will leave the false socket empty. Well, for the condition, I will need the group input here. So let's add the group input. I will need now the Boolean value of eprom window enable. So that will go through a logical AND node. And the second condition will have to be that the pin count is actually larger or greater than the min pin count. So if both of these conditions are met, let's actually plug it like that, the condition of the switch will be true. So let's plug it like that. And if we enable the EEPROM window, and actually greater than or equal to 10 has to be the condition. So anything below 9 will result in a chip without the window. So let's return the window here and disable it on the switch here as well. And anything larger also will not result in the window being visible. Okay, and I see we didn't change the value here for the narrower chip, so we are still at the circular window. So let's change it to 0, 1, so we have that rectangular opening here. And the last thing remaining in this part is to actually place a glass in the cutout. So for that, I will reuse the convex hull shape that we made previously. So if we add here a viewer node, you can see that we have that shape that would fit there perfectly. So let's add here a set shade smooth node. That will be the first thing we will need to do. Then transform the geometry. We will definitely need to transform it somewhere upwards. For that, we will need a combine XYZ vector or combine XYZ node with the vector output. And actually, let's already connect the transformed geometry to the join geometry node somewhere to the bottom. And let's get rid of the viewer so we can actually see the glass itself. Well, I think I will start with moving the glass with half of the chip height. We already calculated it here, so let's just replug that value to the z-axis. And obviously the glass is too thick now, so I will need to utilize a scale elements node. Plug it before the set shade smooth and set the scale to something like 0.25, only well in the single axis mode, and of course not on the x-axis but on the z-axis. So now we will need to move it a little bit downwards with or we will need to subtract something from this. That will be actually, we have to multiply the thickness of the original cutter object with 0.5. So let's multiply it. Okay, half of that because it's lying right on the world origin. Half of that is going down, half of that is going up. So let's multiply that by the 0.5, and we are scaling it with 0.25. So let's actually reuse the value here. Let's enter it into a value node, change it to 0.25, and then multiply this again together. So this one and this one, and that we will subtract from this multiplication. So let's add here a subtract node, connect it actually to the z-axis, and we will be subtracting this value, the result of the thickness, let's say half of the thickness from the translation from the half of the chip height. We have it flat with the top of the chip, and now, although I quite like it, but I will move it a little bit downwards on the z-axis. So let's duplicate the subtract node and enter here a value of 0.15 millimeters. That will insert it a little bit lower. And just like with the cutter object, when the window is actually disabled, let's reuse the switch node, and again If the window is disabled or the pin count is lower than 10, I don't want also the glass to be displayed, so let's plug it on the line and just replace the false socket with the true socket and use the same condition that we used for the hiding of the cutter object. Now I think what I need also to do is to add a set material node, plug it in a bit before the switch, and draw the material socket to an empty socket of our group input, and just realign the order of the inputs. So let's move it closer to the materials, and let's name this material glass. What's next? Well, you know the drill. Let's rearrange it a little bit, just a little bit. I will give it to you as a homework to make that look nicer, a little bit nicer than mine setup does. So let's select everything, go to Node Wrangler, click frame selected, and let's name this as a eprom window. Okay, and also I'll move it a little bit to the side so the line goes a little bit nicer than it went. Okay, now we can go to the shading tab and actually make a new material, name this glass. And we can get rid of the principled BSDF and of all the other nodes here, and actually create a glass BSDF shader, or use a glass BSDF shader with index of refraction 1.47, which is quartz glass. The glass BSDF is quite a lot simpler than the principled BSDF, and we don't need all of that parameters from the principled BSDF. So now let's assign that material to the glass actually, and we need some additional setup. So in the render settings for Eevee, you need to enable the screen space reflections and also the refractions, obviously, and nothing happens because every refractive material also needs to be enabled on per material basis. So go to the material tab, and the settings here enable screen space refractions. And also what you'll need to do is to decrease the refraction depth here significantly. So in case of the window is only, I think, 0.25 millimeters thick, so the number will have to be really low, something like 0.01 millimeter. And now it shows the inside of the chip correctly. So that's our chip with a window. And that's it for today, folks. Thank you for watching until the end. Or did you just skip here from the beginning? Well, shame on you if you did. Go watch the entire series again. I'm just kidding, I'm doing that as well. We are getting close to a finish, but there is still some work to do on this project. What remains to be done? A chip tile with a shader, instances of the tile, and a base for the tile with wide leads. That means in 2 or 3 parts the series will come to an end, sadly. Or is it thank God? So make sure you hit that subscribe button and don't miss any of the remaining parts. See you at the next video.